Section: Introduction. In this section, we discuss the growing need for effective methods to automatically evaluate the quality of generated videos as generative video models improve. While current models can create visually convincing frames, they often struggle with maintaining coherent motion. The traditional method of using human judgments to assess video quality is costly and not scalable for regular evaluations during model training. Existing metrics, like the Frechet video distance, can measure some aspects of plausibility but are sensitive to frame content and require access to the training data, which isn't always available. Moreover, these metrics typically compare entire distributions of videos, leaving a gap in evaluating pairs or individual videos. We propose a new method that tackles these challenges by directly modeling two-dimensional video motion. For a single generated video, we estimate motion features over time using the Boots taper model. We then encode these features into high-level motion representations with our trajectory autoencoder, or Trajan. This allows us to compare video distributions, whether it's one generated video against one real video or two datasets, and to assess motion inconsistencies in individual videos through reconstruction errors. Our point tracking method focuses on the essential features for predicting motion without needing to reconstruct the entire scene, which helps us evaluate plausible motion regardless of the semantic content. We demonstrate that TRAJAN's features are more effective than other methods, such as VideoMay v2 and i3D, in detecting synthetic motion distortions. For pairs of videos, we calculate the distance between their Trajan embeddings, which better reflects motion similarities than appearance-based metrics. For individual videos, we assess how well Trajan reconstructs the original input tracks, finding that this score correlates strongly with human ratings of realism, appearance, and motion consistency across various models. Additionally, we conducted a human study to gather ratings on generated videos, focusing on aspects like interaction quality, realism, consistency, and speed. Although these ratings are somewhat subjective, we found that Trajan generally outperforms previous methods in predicting human evaluations, indicating potential for further research. We categorize existing metrics for video quality assessment into three areas: comparing distributions of generated videos, comparing generated videos to real references, and evaluating individual videos without a reference. While these areas are often treated separately, we present Trajan as a unified model for measuring motion consistency across all three settings. For video distributions, the Frechet video distance is a common metric, but it can be biased towards individual frame content. Other methods, like VideoMay, aim to address this, while some focus on histogram-based motion features from point tracks. Our approach, using learned Trajan features, shows significant improvement. When evaluating paired videos, traditional metrics like peak signal-to-noise ratio and structural similarity index focus on pixel-level discrepancies but often miss the temporal coherence crucial for video realism. Recent metrics for individual videos, such as clip score, primarily assess semantic alignment rather than dynamic properties like motion quality. Our method, based on point tracks, emphasizes motion and appearance consistency, which is vital for aligning with human judgments of video quality. As generative video models evolve, we see a need for robust evaluation benchmarks. We assess Trajan on platforms like VideoFi, which tests models against physical laws, and EvalCrafter, to ensure comprehensive evaluation of generative video capabilities. Section Summary. In this section, we highlight the need for improved methods to evaluate the quality of generated videos, as current metrics often rely on human judgments or are limited in capturing coherent motion. We propose Trajan, a novel approach that models 2D video motion to assess video quality across various settings, demonstrating its effectiveness in predicting human ratings and outperforming existing metrics by focusing on motion consistency rather than frame-level content. Section: Methods. In this section, we focus on methods for evaluating motion in videos by addressing two key areas: extracting latent representations from videos and calculating ordinal metrics that allow us to rank videos based on quality. We introduce Trajan, which provides latent representations and serves as a metric for individual videos. For comparing distributions, we calculate the Frechet distance between the latent representations in two datasets, which helps us understand how similar or different they are. This distance can be simplified to a formula that involves the means and covariances of the datasets when they follow a multivariate Gaussian distribution. For comparing pairs of videos, we use the L2 distance between their latents, and for evaluating a single video, we rely on ordinal metrics like reconstruction error to assess quality. Trajan is designed to work with point tracking models, such as Pips++ or Bootstaper, which effectively track points in various videos. Since point tracks are more related to motion than appearance, they are ideal for assessing motion quality. However, working with point tracks can be challenging due to their unordered nature and the presence of missing data from occlusions. To tackle these issues, we developed the trajectory autoencoder, Trajan. Trajan is trained to reconstruct point tracks from random queries over time and space, providing both a latent representation and a reconstruction score. In terms of architecture, for each track, we first embed the locations using a sinusoidal method and project them into multiple channels. We then introduce a readout token and apply self-attention to all tokens, using an attention mask to ignore occluded points. After this, we keep only the readout token to create a fixed-length representation of each track. We then use a perceiver-style approach to encode all track tokens by cross-attending from a learned set of latent tokens, followed by self-attention. Finally, we reduce the dimensionality to create a consistent representation of the tracks. To ensure our representation captures dense motion, we train it to reconstruct tracks from the video using a decoder. This decoder is designed to be invariant to the specific query points, allowing it to reconstruct tracks that were not part of the input. The decoder takes the latent representation and a query point to output the corresponding track. We enhance the representation and compute a readout token for each frame, where we also train an occlusion logit and position outputs. One of the benefits of Trajan is its ability to evaluate motion directly. Since it was trained on real motions, we expect it to struggle with unrealistic motions, making it a useful tool for assessing motion quality. We propose the average Jaccard (AJ) metric to evaluate the accuracy of the autoencoder's reconstructions against the input tracks. This metric combines occlusion and position accuracy, defining true positives, and false negatives based on a set threshold. The average Jaccard averages these values across multiple thresholds, providing a comprehensive measure of performance. Further details about our training and architecture can be found in the appendix. Section Summary. In this section, we describe our method for evaluating motion in videos using Trajan, which extracts latent representations and computes ordinal metrics for video quality. We also introduce average Jaccard (AJ) as a measure of reconstruction accuracy, combining occlusion and position accuracy to assess the model's performance on real motion data. Section: Alternative Models. In this section, we explore alternative models for evaluating motion in videos, comparing them to Trajan. We consider two motion-based metrics, one using histograms of point track trajectories and another based on optical flow. For motion histograms, we assess motion consistency in generated videos by estimating velocity and acceleration from point tracks. We divide the resulting data into small segments and gather the magnitude of values at different angles. By combining these histograms for each segment, we create a detailed vector that describes the motion in a 16-frame video. In terms of optical flow, we recognize it as a useful method for analyzing motion. This technique estimates flow between consecutive frames, which may limit its ability to capture long-term motion patterns. Previous studies have used warping error to enhance temporal consistency in videos. We calculate this error by comparing the second frame to a warped version of the first frame, taking into account occlusions. We use a refined version of the Raft model to estimate optical flow, focusing on negative warping error as our metric. We also consider appearance-based methods, inspired by FVD, which analyze RGB data directly. However, We note that these methods can be biased towards content, particularly in classification tasks. For the i3D network, we utilize its output from action recognition training on the Kinetics 400 dataset as a feature space for video comparison. We measure video quality using negative entropy from action class predictions. VideoMay, a masked autoencoder trained on videos, is another method we examine. We use VideoMay v2, which is designed to reconstruct missing parts of videos rather than predict future frames. We evaluate two versions, the pre-trained model and one fine-tuned for action recognition. We calculate metrics based on embeddings from these models. Lastly, we look at Moog, a recurrent model for next frame prediction. It updates an internal state to predict the next frame based on image features. We modify the model slightly for simplicity and focus on its prediction error measured by PSNR as our metric. Section Summary. In this section, we explore alternative motion-based metrics for video evaluation, including motion histograms that analyze velocity and acceleration from point tracks, and optical flow that assesses temporal consistency through warping error. Additionally, we discuss appearance-based methods like i3D and VideoMay, which utilize RGB data for video comparison, and introduce Moog, a recurrent model for next frame prediction that captures both appearance and motion. Section: Human Evaluation. In this section, we evaluate the usefulness of our proposed metrics by comparing them to human judgments. We gather detailed human annotations for generated videos, focusing on four key aspects: consistency of appearance and motion over time, realism of object and background depiction, realism of object interactions, and the perceived speed of motion. These dimensions help us identify common issues in generative video models, such as unnatural shape changes, jitter, poor interactions, and implausible scenes. We allow humans to provide ratings on a continuous scale to reflect varying degrees of adherence to these criteria. More details about our evaluation questions and user interface can be found in the appendix. Next, we assess Trajan and other methods in three practical scenarios: comparing video distributions, comparing generated videos to real ones, and evaluating individual video quality. Across all scenarios, we find that Trajan consistently outperforms the alternatives, particularly in detecting motion artifacts. Additional results and experimental details are available in the appendix. When comparing video distributions, we start with the empirical distributions of videos, which is a common approach for metrics like Frechet Video Distance, FVD. We use real videos from the UCF 101 dataset, which contains over 13,000 videos of people performing various actions, and we apply different levels of synthetic corruption. We categorize the corruption into two modes: spatiotemporal, where frames are distorted independently, and spatial, where all frames are distorted using the same parameters. We measure the sensitivity of our metrics to temporal corruptions by calculating the Frechet distance between the latent representations of videos. Our findings show that Trajan is the most sensitive to these temporal distortions. To connect distribution level and single video metrics, we also compute per video metrics and average them across the set. Trajan and the Raft warp error show high sensitivity to temporal distortions, while other methods like motion histograms are less effective. Although distribution comparisons yield the highest sensitivity, TRAJAN's strong performance indicates that per video metrics based on motion can effectively replace distribution-based metrics when reference datasets are unavailable or sample sizes are small. In our comparison of real and generated video pairs, we note that many video models predict future frames based on a few real frames. However, comparing generated and real frames can be challenging due to uncertainties in future content. We explore whether latent space comparisons can better capture realism than pixel-based scores. We train the Walt Video Diffusion Model on the Kinetics 600 dataset to predict future frames based on two real latent frames. We analyze video embeddings from Trajan, VideoMay, and i3D on a set of generated and real samples with significant motion. Our results indicate that distances in latent space do not correlate well with pixel-based metrics like PSNR or SSIM, particularly for Trajan. This suggests that Trajan captures different aspects of video quality, focusing on motion differences rather than appearance. In contrast, VideoMay and i3D are more sensitive to overall recognizability. Thus, Trajan proves useful for measuring motion similarities between videos, even when pixel-level accuracy is not achieved. Section Summary. In this section, we evaluate our proposed metrics against human judgments across dimensions like consistency, interactions, realism, and speed, aiming to identify common failure modes in generative video models. Our findings indicate that Trajan outperforms alternative metrics in sensitivity to motion artifacts, making it a valuable tool for assessing video quality, both at the distributional and individual video levels. Section: Original Eval-Crafter Dataset. In this section, we analyze the Eval-Crafter dataset to ensure our metrics are not biased by human evaluations. We compare our findings with the human ratings provided by the original authors. We noticed that the human judgments in this dataset, which assess aspects like temporal consistency and visual quality, were largely influenced by overall motion. Videos with more motion were rated lower, regardless of how realistic that motion looked. To address this, we re-evaluated the data by grouping videos based on their motion intensity and calculated Spearman rank coefficients for the top half of the dataset, where significant motion was present. Our results show that Trajan significantly outperforms other metrics in explaining both temporal and visual consistency, as well as subjective likeness, indicating it captures more than just the intensity of motion. For the VideoPhi dataset, we further validate our approach by reporting the area under the ROC curve using the original human labels for physical consistency. In this case, Trajan, along with Raft and Moog, are the top-performing models. We also compared our results to Videocon, which fine-tunes a vision language model on a subset of human labels. Notably, Trajan performs exceptionally well without any fine-tuning, demonstrating its effectiveness in evaluating motion across various models and datasets. Additionally, we utilize Trajan for spatiotemporal error localization, allowing us to identify where and when inconsistencies in motion and appearance occur. By calculating reconstruction quality for each point in space over short time intervals, we can pinpoint errors. We illustrate this with a generated video that Trajan rates as highly consistent and another as highly inconsistent. The consistent video maintains a high reconstruction quality score, while the inconsistent video shows significant fluctuations, particularly when the glove's appearance changes. Visualizing the spatial errors reveals that the glove's points contribute most to the low score in the inconsistent video.